So at this point, hopefully you have already seen your Z and E nomenclature system for alkenes, and we'll see a kind of similar system pop up when we look at sp3 carbons, so no alkenes, but have chirality associated with them. So if we take a look at the examples drawn on here, in one case they're actually pointing to what's known as our stereogenic center. So we have a carbon with 4 different things attached to it. That carbon has 4 groups, and their orientations relative to each other are different from one structure to another. So if we went through to name these, we're going to end up having to again come up with a nomenclature system that allows us to tell a difference between them. Okay? May not seem like a big deal for the ones on the far right, but if we take a look through the middle there, that's actually kind of important, because one of those forms of the drug kind of gets rid of nausea, so we don't have to be sick, which is kind of nice. The other form of it, the mirror image of it, is a teratogen, meaning it causes mutations. So that's not particularly a good thing. We might want to make sure that our label or our nomenclature system allows us to differentiate between those two. And it turns out that that nomenclature system is going to fall back pretty hard on this Con Ingold rules and priorities that we used with our ZE nomenclature system. So in case you forgot already, or are now new to the RS system, we have to go back to looking at our priority using this system. Your priority is assigned based on atomic mass. Okay, notice that the atomic is bolded here, because that is important. And the standard notation is to make the highest priority group numbered as 1 and the lowest priority numbered as 4. That is kind of arbitrary. Just realize when we move further on into our rule set, that becomes of critical importance in the assigning process. So I would highly recommend that you follow that standard notation. Remember, higher atomic mass. For those of you that are new to this video and haven't gone through and looked at priorities, what we've got down below are 4 potential groups. So if we take a carbon atom and we bonded 4 things to it, say these 4 things being connected through that bond, okay, we want to decide which of these would be the highest priority, which of these would be the lowest, and everything in between. So take a hot second here to go ahead and figure that out. And now that you've paused and come back to the video and have it figured out, we'll go through and look at our atomic masses. So in our comparison, we are comparing carbon to oxygen to chlorine to carbon. Okay, notice that I am highlighting the atom because these rules follow off of atomic notations or atomic principles. Chlorine, being the highest atomic mass of this set, will be assigned a 1. The oxygen will get assigned a 2. We now run into a dilemma, as we often will when it comes to assigning priorities, between carbon on the left and carbon on our extreme right. To figure out our difference, we have to move to the next atom until we can find a difference. Okay? In a lot of the situations you'll find, you run through carbon atoms that are all sp3 hybridized. There's no real issues with this whole process. What does happen, though, is when we every so often encounter an sp2 carbon, like we do in that first example, which we'll now call our blue example. To fix that, we have to fake it, right? Fake it until you make it. Fake it being sp3. And so to do that, what we'll do is look at that pi bond as kind of a phantom extra carbon. So when we're looking at the atoms connected to that blue carbon dot, we have a carbon, carbon, and a carbon. Okay? So what we're trying to do is just specify what atoms are connected. This can help us see the priorities. If we go through and look at our purple atom, our next highest priority atom is a carbon, but then what is our central atom connected to? Well, 2 hydrogens. When we now go through and compare across our lines, the carbons will cancel because there is no difference there. But then the very next thing we have on the left, our blue carbon, is a carbon, and on our right we encounter a hydrogen. Well, since carbon has a higher atomic mass than hydrogen, our carbon carries the higher priority. It comes in as 3, and our far right carbon comes in at 4. Okay? So that is our official numbering according to our Kahn-Ingold. Some things to watch out for, as we kind of clean this up a little bit, is that there is a tendency for students to go through and say, maybe assign a 1 to that ring. Okay? Maybe even a 2. Maybe you acknowledge that the chlorine carries the 1. Okay? And typically the reason is that you look at that group and say, well, it's really, really big. Okay? Well, big has nothing to do with it. Okay? That's completely irrelevant. What you have to look at is the atom in this case. The atom is carbon. The atom in the next one is oxygen. The atom is chlorine. So you have to be a lot more specific in what you're looking at and making sure to not look at the whole structure, but just as the individual pieces. Sometimes you'll find instructors try to trick you and give you giant pieces to try and trigger this. Look at the atom. Keep your focus at the atom, and then you don't have to worry about it ever again. So, how do we then use this, say, in a nomenclature example? So, first thing we would have to do is identify a chiral atom, because why worry about all these rules if we don't have to? Okay, well, hopefully you can see that we have a chiral atom there. And we'd go through and assign our priorities. Our oxygen comes in as 1. When we go through and look at the other ones, we'd be going out to carbons all the way around. So this makes it a little bit more difficult, but you should be able to determine that we have our second priority here, and that we have our third, whoops, sorry, I did that backwards, and sort of, not really backwards. That last position would be our lowest priority. So typically our extremes are easier to find. But we'd have our second priority over here, and our highest priority, or sorry, third priority over here. And we've now got our priorities assigned, but now the question is, what do we do with that? Okay, and that's where the next step becomes of critical importance when assigning your R and S systems. Okay, just for kind of giggles, take a minute here to go ahead and pause the video and see what you can come up with a name for this one. And when we come back, you'll have the whole structure up there. Ta-da! There's our answer, all put together. So this one's a little bit more advanced as far as our functional groups. You should still be able to process it because you have that full rule set further on, or earlier in the video. So the next still process is coming up with how do we identify the arrangement around that chiral atom. So we need something out front to specify how those atoms are arranged. As you might guess, we will need a 3 to specify the location, but then the question is, well, what are we going to name the next thing? We can't say Z and E because that refers to a double bond. What we'll end up using is this terminology known as our R or our S. So now the question becomes is which one do we assign? Okay, to do that, we have to look at our rules. So, identify your chiral atom, which means an atom with 4 different things attached, or distinguishable things. Assign your priorities, 1 through 4. Okay. Here's where that priority ranking comes in really, really important. You must orient the molecule so that the lowest priority is aimed away from you. That means if you're looking at the structure drawn, okay, so we've got it shown here, your number 4 substituent must be dashed. If it is not dashed, you need to change your viewpoint on the molecule to ensure that you are looking at it where it is dashed. Once it has been oriented in that fashion, you will then connect using kind of an arc your arrows or your numbers 1 to 2, 2 to 3, and look at the direction at which you're rotating. In this case, we are rotating clockwise. Clockwise is assigned this R signifier. Okay, R for right. Okay. If instead, when we looked at our structure, okay, and we'll pick a couple examples of this in a second, we connect from our 1 to 2 and we go counterclockwise, which takes too long to write out, but I'm doing it anyway, i.e. to the left, we refer to this as S. Okay, so that would be the classification we would now put on our stereo center. Okay, some things to watch out for are things that can make this easier. If your lowest priority is already dashed within your structure, great, phenomenal. Just do your clockwise or your counterclockwise rotations. If it is not oriented away from you, then you run into some kind of caveats. I have noticed that other people will go through all sorts of rules, or if you're doing a rotation, that just means you do one change, and it's always confused me. For me, the easiest way to do this, or the most likely way to get the correct answer, is to draw each of the bloody rotations for your structure. I know that is tedious and time-consuming, but it guarantees you the correct answer. Otherwise, you may end up doing the wrong permutation with your RS system. Okay, so let's go ahead and take a look at our next slide, which I believe has some examples. So take a minute here. There's our pause. See what you can come up with, and we'll go from there. Since I already gave you the answers earlier in this video for the one on the right, we'll just kind of ignore that. As for the one on the left, we would go through and assign our priorities. We're comparing carbon, hydrogen, carbon, and carbon. Well, the hydrogen hopefully stands out as the easiest. That's our fourth priority. Between our carbons, which one's our highest priority, we can do our kind of half cheat method. This is an sp2. The less hybridized the carbon, the higher priority, and in this case that does end up working. The next one will be a 2, and the last one will be a 3. Hopefully those were relatively straightforward to nail down. The one on the left is also the easiest one to work with, because we'll notice that our next step is to orient our lowest priority away. Well, number 4, our atom is oriented furthest away. So cool, it's already in that fashion. So what we'll now go through and do is connect with a circle or with an arc going from 1 to 2, 2 to 3, and notice that the direction that I am moving theoretically is counterclockwise. I always get that backwards, but I think I got it right there. Counterclockwise, which means we assign S. So in our name, we would then have to specify the location, position 3. We have the S orientation, so we could say 3S, 3-methyl cyclohexene. For those of you counting, you'll notice I did not specify the location of the double bond in that cyclic structure, and that's because in a cyclic structure, by definition, our highest priority group starts at position number 1. So we can drop the 1 from the name. Those of you also keeping track may have said, well, isn't that a bit redundant to say 3S and then 3? Yes, and our name can be condensed down to actually 3R methyl cyclohexene. And we've now got our structure on the left. Structure on the right, bit nasty, and I'll probably end up having to pause the video, hopefully unbeknownst to you, to deal with this one. If we go through and take a look at this, when we assign our priorities, we have our 1, our 2, our 3, and our 4. Okay. One of the things that we're going to have to be cautious on is if we look at how this molecule is set up, the atom number 4, our lowest priority, is aimed in the plane of the paper, not away. Okay. This is a problem. We cannot assign R and S yet. That bond must be rotated, okay, or must be adjusted in the structure such that it is aimed away from us. Okay. For me personally, this means either 1, building a model and doing the rotation and then assigning R and S, or 2, going through and dealing with some of the structural characteristics that allow the drawing. So because I don't have a model and can't show you that right now, what I'll do is describe the action. I need to get atom number 4 to go backwards. So what I'm going to do is grab this OH and I'm going to pull and rotate about the now blue bond, which means when I go through to redraw my structure, that bond will not have gone anywhere. Okay? In the process, the OH will now be where the 4 used to be, and there's my position 1. Okay. The 3 in this position, in this rotation that was away, will now replace where my 1 position was, and my 4 will then have spun out into the back. Now that I'm looking at my proper orientation, 1 to 2, 2 to 3, I'm going in the clockwise fashion. Clockwise means R, and yes, those of you keeping track, good job. I now just processed, I should say 3S on the other side. I don't know why I said R. Clockwise means R, and our answer becomes our R orientation at the 3 position. Okay. You'll notice that we can't shortcut this one and just say 3R hydroxy 3-methylpentanol, and that's because the 3 refers to the hydroxy, and then separately we have to say the 3 for the methyl. Okay, so we'll have to include the 3R way out in front. The other thing that you could go through and do is say, well, did we have to go through and do that? Okay. Well, if we didn't do that bond rotation, 1 to 2, 2 to 3, we would have said that our structure did a counterclockwise rotation, or the S configuration, which would have been wrong. Okay. There are tricks. If you have to do a single rotation, allegedly you go from R to S or S to R. I've never been able to consistently get that to work. I have to draw it out each and every single bloody time. If you want to make fun of me, by all means, go ahead and do so. Okay. The last little part that we'll look at is that when we look at R and S, you'll notice that there are other views that can come into play here. So one of them comes out from this guy known as a Fischer, or came from Fischer, and he's invented a Fischer projection, much like a Newman projection or line angle drawings or all that kind of fun jazz. So one of the reasons why he developed this is that he was working with carbohydrates in biochem, and there are a lot of stereocenters in these molecules. So he said he was tired of dealing with all these wedges and dashes and just wanted to simplify how we drew it. Okay? So what we've got on the left is a representative example of our carbohydrate. And so what he did was changed his view on the molecule. Okay? And here's the rules on how he's changed his view. We want to orient the carbon chain on our vertical axis, and every atom or the chain will always go away from whatever carbon you're referencing in your axis. I know it sounds kind of weird, but we'll get through that. The highest priority carbon we'll place at the top, and then by definition, if you're looking at it in this proper fashion, you'll notice that your substituents will be forced to aim towards the observer or towards you as wedges left and right. Okay? So if we go through and take a look at this, our first thing to do, so all I've gone through and done in this case, is we took this whole structure, and it might be easiest to think about this guy, and I just kind of pulled it out at you and to the right. Yes. So in that case, if I do that, these bonds are then dashed away, hence the drawing. Okay. If that's all I've done is then pulled that at you, what happens when you then shift your viewpoint to this next molecule? Okay, well, or next atom. Well, to that atom, these bonds are now aimed at your observer. Okay, well, that's not in the proper Fischer projection. Okay, so that means you have to alter the rotation about that bond to get it to align. Okay, so if we just look at maintaining this, we would then go through and kind of stepwise look at each of these rotations. So the first one, perfectly aligned, no issues. The next one, we end up with this kind of odd wedge dash issue. So we have to fix that by doing a rotation. And we do that rotation, we would end up with this. Notice that it appears, quote unquote, that the OH has now shifted sides, but that's because you had to do a rotation about that bond. Okay. The next one, already in the proper viewpoint, so we don't have to do any switches there. And then the last one, we'll end up having to do a rotation again. And so what we've gone through and done is just changed our view on the molecule so that we are now forced to look at it in this fashion. If you go through and build a model kit of, number one, the structure on the left, and then look at it for the middle one, and then look at it for this next one, or for this last one, what you'll notice is that when you then take the structure and flip it back this direction to make it kind of look like our line angle. So don't do any bond rotations, just take what you've now done on your rotations, or your bond rotations to make it look like this, and now just turn it sideways. What you'll notice is that you'll end up with a spiral of a structure. Okay? And it's not easy to show here, but notice that we're showing these start large and then get progressively smaller and smaller. The longer your carbon chain, the more it's going to kind of spiral inwards on itself. Okay? And the idea is that your viewer is looking at your carbons all the way around. So we end up changing our viewpoint almost for every single one of those carbons to generate the Fischer projection. And you may say, God, that's confusing. It is, but it's a whole lot less confusing than our standard line angle if we have tons of chiral atoms to work with. If we don't have a lot of chiral atoms, then our line angle makes sense. If we have a lot, Fischer makes a little bit more sense. And I very grudgingly admit that. Okay, just for the record. So, our last simplification here, because Fischer has defined this as the rule set for how you look at this, we don't need wedges and dashes anymore. Okay? So we then simplify the structure out to what we see on the right, and this is very commonly what you would find in a biochemistry textbook. Okay? You just see the structure written out this way, or in even biology textbooks, because we don't want to have to deal with this, oh my god, three-dimensional space relationships. We can just memorize the arrangement of those atoms off of some straight lines. Bunch of load of nonsense, but whatever. Okay. The next part of this that's going to throw an extra wrinkle into this, what about the RS determination? Okay, remember, when we assigned our R and S, we had to make sure that our lowest priority was aimed away from you. If we look at our Fischer projection, our lowest priority in each of these cases where we have a stereocenter is the hydrogen, and it's aimed at you. You're looking at it backwards. Okay? Well, that just means that your assignment is backwards. It's perfectly out of sync. So what you can go through and do is just assign your priorities. So we would go through, for that first one, we have 1, 2, 3, 4. When we go through to count, that would say we're going in a counterclockwise fashion, but it's Fischer projection, so everything is backwards. It must be R. Okay? So we end up doing a real quick switch from S to R. Okay? Interesting thing to note, remember what we said R was? We said R was right. Well, where was our highest priority substituent? Interesting. Interesting. How about the next one? We go through and assign the next one. We've got our 1. This will be 2. Whoops, that's a 3. That'll be 4. 1, 2, 3. Okay. That would say right, but we're looking at it backwards, so it becomes S. Interesting. We swapped it to the other side, and all of a sudden became S. Very, very puzzling. If you go through and test this all the way out, what you'll find is your highest priority group, if it is located on the right-hand side of the structure, is miraculously the R configuration. If it is the left-hand side of the structure, it is the opposite, RS. Pretty cool. So, again, Fischer simplifies this so that we can now do this assessment. One of the things you have to watch out for is you must be in a Fischer projection. You have to be following all of the rules that we had outlined on this previous slide. Okay? If these rules are not met, then our little abbreviations of what's on the right and the left isn't going to work. Okay? So watch out for that. Last thing, you'll see a tiny little note in that left hand, or sorry, that's my right hand corner. We got to be careful when we look at chirality. So far what we've addressed is this idea of R and S. Okay? This is by looking at the structure. Okay? So this is a structural determination. An issue with a structural determination is that we can't see the structure. So if we think back to the lecture, how did we see that we had a chiral molecule? Well, then we looked at optical activity. And optical activity, that says optical activity, we could look at plus or minus And we could also potentially look at lowercase d or lowercase l. Okay? Also pretty nice. If we think about the relationship between R and S and plus and minus and D and L, there's lots of clockwise and counterclockwise. And everyone goes, oh, well, we can start to make comparisons. No, 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 no. No, you can't. Don't do that. Different system. Okay? Optical activity does not tie to R and S, so don't make those connections. The optical activity is an experimental observation. R and S is a structural determination. Entirely different systems. So don't be making that mistake. Okay. Well, Fischer went through and came up with his new system with this idea of capital D and capital L. So, well, that looks awfully similar to this lowercase d and lowercase l, and that could potentially be back to our R and S system. And we go, oh, well, now we have a comparison. No, 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 no. These are three entirely different systems. Do not overlay them. Okay? They do not mix. There's reasons for assigning capital D and capital L. Those reasons are different from assigning capital R and capital S, which are different from assigning plus and minus, which may even be different when assigning D and L. Okay? So I know chiral has all of these different ways that we can go through and assign things, and it's very tempting to try and overlay them. Do not do that. Okay? Last thing we'll bring in here, just as kind of, well, it's not really a happy thing, but if we think back to Fischer and go, well, why bother to go through and deal with this whole extra rule set for Fischer projections? Well, this is what Fischer was looking at. Okay? This is a family tree of your ketone, or sorry, your carbohydrates that have aldehydes within them. Okay? And I don't think this even includes them all. Okay? Add on top of this that we also have the ketone form of these. Okay? So we have a ton of different carbohydrates. We need a quicker and easier way to evaluate them than assigning R and S or even looking at optical activity. Okay? So that's why his system was developed. It is important. We do have to acknowledge its usefulness. In this class, we probably won't see it that much. In biochem, it will come back to potentially haunt you. So know the rules. Make sure you follow them. Go all the way back to that rule set. Make sure you're following these rules. Get used to that kind of familiarity with it, and hopefully you'll be good. Thanks for listening.